Welcome to the Pre-Calculus Notes for Essential Skills C2, Graphing and Limits. In this section, we're going to take what we've been doing with graphing and limits and apply them to exponential and logarithmic functions. Let's take a look at what these graphs look like. You have seen these before in Algebra 2, but a refresher can't hurt. The first thing you should immediately notice is that both graphs have one-sided asymptotes, one horizontal, one vertical. The next thing you may notice is that these graphs are inverses of each other. If you'll notice, all the anchor points have the x's and y's reversed. The graphs I'm showing assume a base of 2. When the base changes, the graphs will look a little bit different, but one thing does stay the same. We have an anchor point of 0, 1 on the exponential graph because anything to the 0 power is 1. Similarly, we have 1, 0 on every logarithmic graph, regardless of base, because the log of 1 in any base is 0. On the parent function, our horizontal asymptote is at y equals 0, and our vertical asymptote is at x equals 0 on the log graph. When you graph natural log, you'll be dealing with some irrational numbers. So we just use our best estimate. Here are our best estimates. E is approximately 2.7. That means 1 over E is between 1/2 and 1/3, and it works out to about 0.4. E squared, if we square this, it's about 7.4. Again, these are just guidelines for estimating. The grids aren't going to provide even this much resolution, so just get close. After doing section B5, you should be able to figure out these limits based on the graphs themselves. Take a moment to pause the video and try it yourself. We'll see how you do. Here are the answers. Now we'll look at some graphs. I'm going to use a strategy that I've recommended to people for complex graphing. There are lots of transformations happening here, so I'm going to start with the table of values, modify the table of values, and then offset it from the new center. Let's start with the parent function. Next, I'll identify the stretches and create a second table with those stretched transformations. Remember that input transformations have an inverse effect. Now I multiply the values in the original table in order to get the new table. Remember that these are offsets from the new center. To find the new center, I look at the shifts. At this point, draw the asymptote. Remember that all exponential functions have a horizontal asymptote that passes through the new center. Now I plot these stretched offsets. Left 2, up 1.2. 0, up 3. Over 2, up 8.1. Then right 4 and up 22, that's off grid. This is enough to show us where the exponential curve is going to be. By knowing the shape, I know how to connect these dots. And the graph's done. Now, these limit statements can be found by looking at the graph. As x decreases without bound, the y value stabilizes at -4. It follows the asymptote. To the right, y increases without bound. Next, we'll look at an example that has some flips and a fractional base. We'll start the same way. Our initial parent function is going to be y equals 1/3 to the x. After throwing in the standard points, it becomes clear that we may want to add -2 as an anchor point. Next, we identify and apply any stretches or flips. Our new center is -2, 1. We always have a horizontal asymptote, no matter how many flips we do. So from the new center, 1, -3, 0, -1, -1, -1/3. I'm not going to try to plot -1/9. 2, -9. And that's enough to plot. Our left side end behavior limit is at that horizontal asymptote. And our right side limit is -infinity. Now let's look at some log graphs. We're basically going to be using the same strategy, so we'll start with the table of values. Tables of values for log functions can be a little more challenging to populate, and so I recommend switching it into exponential form. And letting your y values drive the table. Next, we'll look at our stretches and flips. In this case, we're only modifying the y-coordinate. We only have an output transformation. Our new center is 5 to the left and 4 down. And the first thing we do is draw our vertical asymptote through that new center. Now we can plot. Right 1/3, up 2. Right 1, up 0. Right 3, down 2. Right 9, down 4. And that's enough to tell us how this log curve is going to behave. We can read our limits. The left side has nothing. It literally does not exist. The right side of our asymptote, y values are headed up and up and up. Our limit will be positive infinity. There is no general limit because the left side doesn't exist. And then our right side limit, we are descending, albeit slowly, to negative infinity. The last example ties everything together. It's a good one to try on your own if you haven't tried one yet. Here's my solution. Don't forget the inverse relationship that input transformations have. Well, when we look at the limits, it looks like I made a typo here. By the time I print these, I will have fixed this typo already. I'll go ahead and put the answers. Finally, we'll look at a way to look at limits that does not require us to graph them. To do that, we're simply going to analyze the components. When we see an e to the x in one of these complex expressions, remember that the limit as x goes to infinity is going to be something very large. This will approach infinity. If we have e to the minus x, remember that this is really 1 over e to the x. So if x gets very large, only the denominator is getting large. We're talking 1/1,000,000th, 1/1000,000th, and so the overall value of the fraction is approaching 0. It's getting very, very close to 0. We're going to use these to look at what happens to parts of these expressions. E to the x is going to be getting extremely large. It's headed toward infinity. So the limit of 1 over something very, very large is just going to be 0. Similarly, we know that if x is getting very, very large, this term is going to become insignificant. So this is just going to be 1 plus 0, effectively, or 1. Similarly, we have e to the minus x. That's headed towards 0. This will be 400 over 2 plus 0, which is just going to be 200. Finally, e to the minus x goes to 0. And so our limit is 5/3. The last thing we're going to look at is something similar to the rational function trick. That was where we looked at the lead coefficient when the degrees were the same. Recall that we figured that out through long division. We can do something similar here. To get 3 to turn into 5, we need the 3 to cancel and the 5 to remain. So that'll just be 5/3. The rest is remainder. So this is going to have a horizontal asymptote at y equals 5/3, which means that our long-term limit is approaching that asymptote. Again, we look to the lead coefficients for the shortcut. We can use a combination of both of these types of reasoning because we know that e to the minus x, when x gets large, is going to approach 0 and become insignificant. If we look at the lead coefficient, we're going to wind up with 2/5. In the last example, we have a different case. We can't talk about degrees because this is not a polynomial, but we can see that the order of the denominator is much larger. It becomes more clear if we use exponent rules to rewrite it. So while the numerator varies with e to the x, the denominator varies as e to the x squared. So the numerator becomes insignificant compared to the denominator. It's like x plus 2 over x squared minus 1, at least in that it will have a y equals 0 horizontal asymptote. So the limit is 0. Thanks for watching.